Hello, everyone. In this section, we will introduce the current equation of the p-n junction in electronics. In the previous section, we introduced that once a p-n junction is formed, even without any external bias, there is already a built-in electric field and a built-in voltage, V0, inside the p-n junction. This built-in field and voltage come from the diffusion and recombination of majority carriers in the p-type and n-type semiconductors, which create space charges in the material. The built-in voltage is related to the doping concentrations. Once the doping concentrations are determined, this built-in voltage can be calculated. Next, the space charge region widths in the p-type and n-type semiconductors, xp and xn, as well as the total space charge width w, can also be calculated. Finally, the junction charge, Qj, can be obtained. From the equations, we can see that the space charge width is proportional to the square root of the internal voltage V0. Next, let us look at what changes occur in a p-n junction when a bias is applied. First, a p-n junction is a two-terminal structure. If the p-type semiconductor is connected to a relatively low potential and the n-type semiconductor is connected to a relatively high potential, as shown in the figure, this biasing condition is called reverse bias. The reverse bias voltage is VR. When a reverse bias VR is applied to the p-n junction, this voltage difference generates an applied electric field, E applied, inside the p-n junction. The direction of the electric field is from the higher applied potential to the lower applied potential, which means from the n-type semiconductor toward the p-type semiconductor. This applied electric field has the same direction as the original built-in electric field, EBI, of the p-n junction. Electric fields are vectors that can be superimposed. Therefore, the total electric field inside the p-n junction becomes stronger. A stronger electric field also means that the amount of space charge increases because electric field strength and charge are related. If the amount of space charge increases, the width of the space charge region becomes larger. Therefore, the space charge width in the p-type semiconductor increases from xp0, the width without bias, to xp. The space charge width in the n-type semiconductor increases from xn0, the width without bias, to xn. The total space charge region width increases from w0, which equals xp0 plus xn0, to w, which equals xp plus xn. As the space charge width increases and the total internal electric field increases, the total integral of the electric field across the space charge width, which is the internal voltage difference, also increases. As shown in the figure, the total voltage increases from V0 without bias to V0 plus VR. Because the total voltage inside the p-n junction increases from V0 without bias to V0 plus VR, both the space charge width and the amount of space charge increase. This is because both are proportional to the square root of the total internal voltage, as shown in the equations on the slide. After introducing the changes in a p-n junction under reverse bias, let us now look at the case where the p-type semiconductor is connected to a relatively high potential and the n-type semiconductor is connected to a relatively low potential. This biasing condition is called forward bias. When a forward bias VF is applied to the p-n junction, this voltage difference generates an applied electric field, E applied, inside the p-n junction. The direction of the electric field is from the higher applied potential to the lower applied potential, which means from the p-type semiconductor toward the n-type semiconductor. This applied electric field is opposite to the original built-in electric field, EBI, of the p-n junction. Electric fields are vectors that can be superimposed. Therefore, the total electric field inside the p-n junction becomes weaker. A weaker electric field also means that the amount of space charge decreases. If the amount of space charge decreases, the width of the space charge region becomes smaller. Therefore, the space charge width in the p-type semiconductor decreases from xp0, the width without bias, to xp. The space charge width in the n-type semiconductor decreases from xn0, the width without bias, to xn. The total space charge region width decreases from w0 to w, which equals xp plus xn. As the space charge width decreases and the total internal electric field decreases, the total integral of the electric field across the space charge width, which is the internal voltage difference, also decreases. As shown in the figure, the total voltage decreases from V0 without bias to V0 minus VF. Because the total voltage inside the PN junction decreases from V0 without bias to V0 minus VF, both the space charge width and the amount of space charge decrease. This is because both are proportional to the square root of the total internal voltage, as shown in the equations on the slide. After discussing the space charge region width, the total internal electric field, and the voltage difference with and without bias, we will now focus on the carrier concentration changes in the neutral regions. In other words, we will look at the behavior of electrons and holes. First, let us examine the state of the PN junction when no external bias is applied. As introduced earlier, in a neutral p-type semiconductor, the concentration of the majority carrier holes, pp0, is approximately equal to the doping concentration, Na. The concentration of the minority carrier electrons, np0, is equal to Ni squared divided by pp0 and is approximately equal to Ni squared divided by Na. For a neutral n-type semiconductor, the concentration of the majority carrier electrons, Nn0, is approximately equal to the doping concentration, Nd. The concentration of the minority carrier holes, Pn0, is equal to Ni squared divided by Nn0 and is approximately equal to Ni squared divided by Nd. Therefore, we can obtain the carrier concentration distribution shown in the figure on the right. Under thermal equilibrium, which is the stable state without bias, the carrier concentrations in the neutral regions are uniform in space. When a forward bias is applied, meaning that the p-type semiconductor is connected to a relatively high potential and the n-type semiconductor is connected to a relatively low potential, an applied electric field, E applied, is generated inside the PN junction, as shown in the figure. This applied field exerts forces on the majority carriers, that is, holes in the p-type semiconductor and electrons in the n-type semiconductor, pushing them toward the space charge region. These forces are labeled F hole and F electron in the figure. As majority carriers move into the space charge region, part of the space charge is neutralized, so the space charge region becomes narrower. This is consistent with the previous discussion that the depletion region width decreases under forward bias. In addition, the majority carrier holes in the p-type semiconductor are pushed by the applied electric field and injected into the neutral region of the n-type semiconductor. As a result, the minority carrier hole concentration in the n-type semiconductor increases significantly, as shown in the figure. At the boundary between the n-type neutral region and the space charge region, where x equals xn, the minority carrier hole concentration rises from Pn0 without bias to Pn0 times exponential of QVF divided by kT. The concentration increases exponentially with the applied bias. This is the result of majority carrier injection from the p-type semiconductor. At the boundary between the n-type neutral region and the space charge region, where x equals xn, after the minority carrier hole concentration increases exponentially, it immediately diffuses toward the lower concentration region inside the neutral region because the concentration is non-uniform. During this diffusion process, the extra minority holes encounter majority carrier electrons and rapidly recombine, so they vanish. Finally, we can obtain the minority carrier hole concentration equation inside the n-type neutral region, as shown on the slide. Compared with the minority carrier concentration Pn0 without bias, the extra injected minority carrier concentration, Pn at xn minus Pn0, decreases exponentially with position. As mentioned earlier, this is caused by recombination. In the equation, Lp is the diffusion length of hole. Physically, it represents the distance a minority carrier can diffuse before recombination. Lp is equal to the square root of dp times tau p. dp is the hole diffusion constant, and tau p is the hole lifetime, which represents how long a hole can survive before recombination. Therefore, the distance that minority carrier holes can diffuse before recombination is related to both their diffusion ability and their lifetime. The longer they live, the farther they diffuse. The stronger their diffusion ability, the farther they diffuse, and the longer Lp becomes. Therefore, after obtaining the minority carrier hole concentration equation, we can substitute it into one of the two current mechanisms introduced earlier, the diffusion current density equation. The hole diffusion current density at x equals xn is negative q times dp times the gradient of p with respect to x. After substituting the concentration equation, we can obtain the whole current density equation in the N-type semiconductor. After obtaining the whole current density equation in the N-type neutral region, we can use the same idea to obtain the electron current density equation in the P-type neutral region. As shown on the slide, this is the electron current density equation in the P-type neutral region. Finally, we add the electron current density and the whole current density together to obtain the total current density. Therefore, the total current of the PN junction equals the junction area A multiplied by the current density, Jp diffusion plus Jn diffusion. After substituting the electron and whole current density equations, the voltage-dependent term, exponential of QVF divided by KT minus 1, can be factored out. The remaining coefficient is A times the quantity QdPpN0 divided by Lp plus QdNNp0 divided by Ln. Let us pay special attention to this current voltage equation of the PN junction. Other than the voltage-dependent term, the coefficient mainly contains semiconductor material parameters, including the diffusion constants dP and dN, the diffusion lengths Lp and Ln, and the minority carrier concentrations Pn0 and Np0 under thermal equilibrium without bias. The minority carrier concentrations under thermal equilibrium without bias are then substituted into the equation. This gives the equation shown on the slide. Then, the common term Q times Ni squared can be factored out. This gives the equation shown on the slide. We define the area and material constant terms, excluding the bias term, as a coefficient called Is, the saturation current. In the bias term, Kt divided by Q equals Vt, which is the thermal voltage. It is worth noting that this saturation current, Is, is proportional to the junction area A and to the square of the intrinsic carrier concentration, Ni squared. In the previous section on basic semiconductor properties, we mentioned that Ni squared is a strong function of temperature. This means that the diode current is also a strong function of temperature. In general, Is is very small, usually between 10 to the negative 18th and 10 to the negative 12th amperes. The final current voltage equation of the PN junction is IPN equals Is times the quantity exponential of Vf divided by Vt minus 1. During the explanation, we mainly use the forward bias case with Vf to understand the concept. Then, what about the current of the PN junction under reverse bias? As introduced earlier, under forward bias Vf, the minority carrier concentration at the boundary between the neutral region and the space charge region is the thermal equilibrium carrier concentration multiplied by exponential of QVF divided by KT. Therefore, under forward bias, the minority carrier concentration increases exponentially. The polarity of the reverse bias Vr is opposite to that of the forward bias Vf. Therefore, if we substitute negative Vr for Vf in the equation, we can understand the carrier concentration distribution in the neutral region, as shown on the slide. At the boundary between the neutral region and the space charge region, the minority carrier concentration decreases exponentially with reverse bias. At this time, the carrier concentration inside the neutral region is actually higher than the concentration at the boundary between the neutral region and the space charge region. Therefore, the minority carriers instead diffuse from the inside of the neutral region toward the space charge region. So we can understand that for a PN junction under reverse bias Vr, the junction current is Is times the quantity exponential of negative Vr divided by Vt minus 1. This has the same form as the forward bias equation. Therefore, we can write the current voltage equation of the PN junction as IPN equals Is times the quantity exponential of V applied divided by Vt minus 1. Here, V applied is the bias voltage applied to the PN junction. If V applied is greater than 0, it is forward bias. If V applied is less than 0, it is reverse bias. The current voltage characteristic curve is shown in the lower right figure on the slide. When the applied bias is forward bias, and the applied voltage is greater than several thermal voltages, Vt, then exponential of V applied divided by Vt is much greater than 1. Therefore, the forward bias PN junction current is almost directly proportional to exponential of V applied divided by Vt. It has an exponential relationship with the forward bias voltage V applied. Thus, when a PN junction operates under forward bias, its current increases exponentially with the applied voltage. When reverse bias is applied to the p-n junction, V applied is negative. If negative V applied is greater than several thermal voltages, Vt, then exponential of V applied divided by Vt is much less than 1, and exponential of V applied divided by Vt minus 1 is approximately negative 1. Then the reverse bias current of the p-n junction becomes a saturation current, Is. This is why Is is called the saturation current. The reverse bias current of the p-n junction reaches a saturated value of Is, as shown in the current voltage curve. Since Is is extremely small, only about 10 to the negative 18th to 10 to the negative 12th amperes, the p-n junction can be regarded as non-conducting under reverse bias, while under forward bias, the current increases exponentially with voltage. That concludes the introduction to the current equation of the p-n junction. Please look forward to the next class. See you next time. Bye-bye.